is going to be Sandy Walsh, and he's going to be talking about OpenStack.
Thanks very much. So yeah, Sandy Walsh. I'm a geek in Nova Scotia and been programming in Python for probably about 10 years or so. I've been involved with the OpenStack project for about 2 years, and it's an interesting project. It's a very rapidly growing project. I don't know if anyone familiar with any of these names? A few. Okay, good. So some people have used OpenStack then. Okay, good. Virtualization. Anyone using like Amazon services or? Okay, good. We're going to get into some fun stuff then. And I'm from Newfoundland. I tend to talk rather quickly, so if you have any questions, just throw your hand up and yell it out. I mean, you don't have to come up to the mic if that makes you uncomfortable, or if there's something just not making sense, just scream it out and we'll adjust accordingly. So I guess the first thing to talk about with OpenStack is what it's not, because the cloud is a really overused term, as we all know. Everyone's got a cloud and everyone's in the cloud, and no one really knows what the cloud actually is. So one thing that you often hear about the cloud is that these are cloud services, or Wave, or 500 pixels. You know, they're all cloud services, which is true. These are the applications that sit on top of the cloud. But like I say, these are the applications, and a lot of times companies like these will end up building all of their own infrastructure underneath it to make it work, because they had to. They started off with something that worked, and then they had to grow it and get it going. The other side of it, though, is that we're also not talking about the hardware. We're not talking about the motherboards and the racks and all this sort of stuff. If you are interested in open source hardware around data centers, look at the Open Compute project. This is something that Facebook has got going, where they specify data centers, they specify hardware, power supplies, cooling systems, everything. It's a really cool effort, but again, that's not what we're talking about here. What we're talking about with OpenStack is the fabric of the cloud. We're talking about this whole part of it here, which is really the compute nodes, which are hypervisors. People familiar with hypervisors? Virtualization? Okay, cool. So for those that aren't, hypervisors are, it's a piece of software that runs typically right on the bare metal of your machine. And most modern processors have instructions for quickly switching between running processes. So you can basically have multiple operating systems running on one chipset. So an example of that might be Zen Server from Citrix, or there's VMware, there's a whole bunch of different ones. And these are all hypervisors. So they allow you to completely partition all your different applications. And now the kernels of most operating systems have special instructions in it to work with hypervisors, so you get all that security, so that server A cannot see server B at all. They're completely locked down. So that's the hypervisor, but we're talking about the storage, the hard drives, we're talking about the managed switches that make all the networking work, and that's all the stuff that you would normally have to deal with yourself. You've got to set up the racks, you've got to get your networking going, you've got to get all your CPUs and everything going. So all that headache, that's what OpenStack is meant to deal with. The management of that. And it's the code. It's the code that makes it happen. It's not the hardware. And it's Python. OpenStack is 100% Python. It uses some other systems, like it'll use MySQL, it'll use RabbitMQ, it'll use other mechanisms, but all the core infrastructure is Python, and they're quite religious about that. A lot of times there'll be existing packages that are already available, but it generally won't make it into the stack because it's not Python. So we use a fair bit of it. These are just some of the libraries. The main ones in here are Eventlet, Kombu, the Greenlit stuff. There's a fair bit of stuff in there. But I'll get into all that in a little bit. SQL Alchemy. So I'll tell you a little bit about how it got started. So a couple of years ago, Rackspace had bought a company called SliceHost, and SliceHost is a hosting company. Really cool stuff, nice software, and it was all based on this sort of technology. The idea of having a hypervisor and sewing together the networks and making it all work. And it worked kind of well. You could turn the knob and get another 200 servers if you wanted, or another 300 servers. But that's about when it broke down. If you wanted to go any more than that, you got into trouble. Another one here is the cloud servers, or the cloud files, I'm sorry, which is basically your CDN, your storage of data up in the cloud. And that was another product that Rackspace had, and they were going to open source all this. At the same time, NASA was working on a cloud computing project because they had a similar type problem. They had all these different scientists that were working on things, and they wanted to have their own data center, and they wanted to have their own servers, and they wanted to be able to spin stuff up. And the IT department was just run crazy trying to keep up with all these different departments, wanting to have all these stacks of computers. So they started working on a thing called Nova Cloud Compute, and they were going to open source that. So the two groups got together, they got the chocolate, they got the peanut butter, they got together and made a wonderful, tasty treat. But anyway, so they called it OpenStack, and they took the best pieces of both. They dropped the slice host code, which was all based in Ruby, not because it was Ruby, but only because the architecture had grown beyond all capacity. There was just no way it was going to go any further. And NASA said, well, that's cool, you can turn the knob and get 200 servers, but we want to turn the knob and get 5,000 servers. We've got Hubble data coming down, and we want to do image processing on it, and we want to do all sorts of funky stuff. So it's got to scale a lot bigger. So that was the impetus behind OpenStack. And the two main pieces are called Nova, which is the compute side of it, and Swift, which is the data storage side of it. And that's where it started. There was a lot of pushback against that sort of partnership initially. NASA sort of stepped away from it afterwards. They just wanted to become a consumer of this. And Rackspace, of course, is a hosting company, so they wanted to use it, but that's not where they make their money. They make their money off of service, right? So you have something go wrong, you phone them up, 2 rings, you get a human being, and they walk you all the way through the problem. That's where they make their money. So, but people pushed back against that. They thought, well, this is too much ownership for one company to have. Rackspace is, going to dominate this project. So, and there was a lot of companies got involved with it, and they created the OpenStack Foundation. And this is a serious foundation. To become a platinum member in it, it's got a $5 million operating budget annually. I think it's $500,000 to become a platinum member in the foundation. It's serious. So we've got HP, we've got Dell, we've got Intel, Canonical, Red Hat. There's just a raft of big companies that are involved with it because of the lock of Amazon. Amazon does a great job. It's an awesome cloud storage system, a cloud infrastructure, but it's a private cloud. And people want to be able to run this in their office. They want to run a cloud in their basement. They want to have access to it. So the foundation was started, and there's a whole different group there's a technical committee, the board of directors, and then the user community, and the numbers are growing like crazy in this. I'll talk about that in a little bit, though. So there's the sort of the core projects. I mentioned there was Nova, I mentioned there was Swift. There's a metadata layer that sits on top of that for images. So one of the problems you have is you've got these images, like an ISO file for your operating system that you want to spin up into a server. When I say server, we call them instances, just like an instance of a class. So it gets a little confusing. If I say the word instance, I'm talking about a server, but it's a virtual server. So for all these images, we store the ISO files essentially in Swift, but we put all the metadata around it for the images, like say which operating system is this and what patches are on it and all that stuff that you need to know. So Glance does that. And then there's this thing that we loosely call FutureStack, which are not part of the core projects, but they're sort of on the fringe. They're sort of optional pieces. Ceilometer is a billing service because you got to be able to bill for this. This is a multi-tenant package. So you can have multiple companies coming in and using the cloud services. So I can have company A and I can have company B, and the two will never see each other. So Ceilometer is for billing if you're a service provider. Horizon is like an admin interface for creating servers. Keystone is authentication. Quantum does the networking. The networking side of this is really hard. Typically what happens when you get a server, you get a public IP address and you get a private IP address. And then if I have multiple servers, I may not want to put a public IP address on the other servers, so I want all the private networks to just magically work behind the scenes. So that's all got to happen in there. So Quantum takes care of a lot of that. And then Cinder block storage, so Cinder block. But if you want to do block storage and stuff, so SSDs and that sort of stuff is pretty slick. And it's open. And when I say open, it's truly open. It's not just open source where you can get the code, but it is open source. It's Apache license. You can use it. It's open design. So if you have something that you want to contribute to it, you can make a blueprint and you can say, here's where I want to go with this. I want to do this thing. And the core community will look at it and go, yeah, that makes sense. Go ahead, right? Anyone can contribute. You don't have to do a blueprint. If it's something big, then you might want to do it and just say, here's what I'm proposing, but what will happen is generally people will look at it and go, oh yeah, well there's another group over here doing something similar, you should talk to them, and it's really a dating service is what the blueprint is really all about. But anyone can contribute a patch. So you can upload branches, you can get your submissions put in. And because there's a lot of these projects, this is a big piece of software, so because of all these projects, there are technical leads in charge of every project, and you can work within those groups. So if you're really interested in authentication, you can work with a Keystone group. If you're interested in file storage, you can work with a Swift group or a Glance group, and that's how we sort of partition it up. I hate mission statements, but this is a good one. So to produce a ubiquitous open source cloud computing platform that will meet the needs of public and private cloud providers regardless of size by being simple to implement and massively scalable. That's the marching orders. That's every piece of code that we write has to go towards that. But I think I highlight the wrong words in this. Really the interesting part of it is the public and private clouds. The idea of having a data center in your basement. If you've got a machine that you can access, then you can put OpenStack on it, and you can test load balancers. You can put layers of varnish in front of it, and you can do all sorts of caching stuff and experiment with a lot of this stuff. And all the scripts and everything that you write against that private cloud, you just change the URL and point to a public cloud, and it all still works. So that's a really attractive feature for someone who wants to make a startup or wants to grow their business, where they can do something locally and then grow it up into something larger. And the reason, the way that this is a lot of servers here. So we started off very early with our scalability rules and our design rules, what we call our design tenants. So scalability and elasticity are the main goals, right? This thing's got to scale, and I'll talk about scale in a second. So any feature that doesn't allow number one to happen has to be an optional component. And if you look at the OpenStack code, there's a lot of optional components. Everything is basically a plugin. You can change modules and put your own drivers in, do all sorts of stuff like that. There's a lot of that sort of stuff in there. Asynchronous is very important. If you can't do it, make it optional. Horizontally scalable, you can always throw more memory or more disk at a server, but that's not a long-term strategy for scaling out. You have to be horizontally scalable. I'll get into architecture in a second. Share nothing architecture, having mutable data and having state will kill your architecture. So you want to be able to manage state and like I think point 6 says, wherever your logic or your state is, or wherever your state is, put the logic for it very close to it, so it doesn't have to go all through the network to find it. And eventual consistency is key. Don't assume that everything is going to be accurate from the minute that you write it out to disk. It's going to propagate. It's going to there's a flow, a ripple effect of the data as it goes out, and that's the way it has to be designed in order to get there. And of course, tests. You can't submit anything without unit tests. There's unit tests, there's integration tests, there's every level of tests in the system. So the mandate is 1 million instances, so 1 million servers. That's a huge number, and we sort of go, yeah, 1 million instances. That's not really going to happen, but we're getting there. When we first started, 20 instances was sort of risky, and it fell over and it broke a lot. But then we got to 50 instances, and then we got to 100 and 200 instances. Then we got to 1,000 instances. Then we got to 10,000 instances. And we're in production. Rackspace, if you get a server on Rackspace now, you're running on OpenStack. We've probably created 1 million instances, spun them up and tore them down, but we've probably spun up about 1 million servers to date since August. And about a 99.97 uptime. So that counts 500ths on an HTTP request. So, but we want to get to 1 million live running instances. That's where we had to get to. So we're at about, we're in the tens of thousands now. Eventually, we'll be at the hundreds of thousands. And when we get to the hundreds of thousands, then a million doesn't look that far off. But the way we do it is just like this. We just code it, find out what breaks. Something breaks, we patch the link, we go at it again. And rinse, repeat, just do it over and over again. So if typically we can if you've got a good honking server, bare metal server that you can run the stuff on, we figure you can probably get around 200 instances on a server. Let's say, by the time this thing gets to 1 million instances, maybe the hardware will be there for that. There'll be enough RAM or enough disk to do it. So to get to that, we've got to manage around 5,000 compute nodes. These are the things that run OpenStack, run the hypervisor. So think about that. That's 5,000 servers, physical servers that you have to be able to manage. Not even talking about the switches and the racks and all the other stuff, the database and everything that has to go around that, and the activity that's going to hit it. So what happens then if it turns out our hardware isn't that good? What if we can only get 50 instances per server? Well, now your entire architecture changes. Now you've got to be able to scale even, you've got a lot more network switches. You've got a lot more racks to deal with. So whenever you write a piece of code for this, it's very important to think about, well, what are the ramifications of me just opening a socket to that server? Because that's going to be replicated out to every server in the system. I'm just going to poll for this piece of data. Well, you can't really poll for that piece of data because every service is going to be polling for that piece of data. So all those design decisions have to be taken into account. Fortunately, we've got some really smart people working on every major group of it, and they deal with scalability separately. So the Keystone group, the Swift group, the Glance group, the Cinder group, they figure out where caching has to go, where replication has to go, all these different areas as our PTLs. And the rule for OpenStack, if you're a contributor, is code walks. I mean, that's it. You can write big dissertations, you can make your white papers, you can put your proposals out on the mailing list. Someone might respond, they might not. Code always gets attention. If you submit a branch, people will respond to it and say, oh yeah, I see what you're doing there, and here's why it's good and here's why it's bad. So there's not a lot of, there's process, but there's not a lot of heavy process. It's very quick, and code goes a long way. So let's talk about the architecture. How do we get to where we are right now? The very first piece is that you've got an outside client that wants to get in. So there's a web interface, an HTTP interface on this, a REST interface. And the very first thing that it has to do is it has to authenticate. So this is where Keystone is up here. And it'll talk to Keystone and it'll say, okay, I want to authenticate, here's my credentials, and it'll get a token back. Now it's got the token. And then in with the token, there's another piece called the service catalog. And it's just a JSON structure, and the service catalog says, here's all the resources that are out there. So now I can look through it and say, oh, here's my compute node, here's my API node, here's all my other stuff that I can get to, my Glance server. So typically you'll talk to an API node. And there's different APIs on OpenStack. We've got an OpenStack API, which is sort of a variation on the original Rackspace one. But also there's EC2. So if you're an existing Amazon customer, you can use an Amazon-like interface to do all the same sort of stuff. And there's other groups making other APIs that are more standards-based, and they can plug those in as well. And when I say EC2 compatibility, it is an EC2 compatible API. It's not bug-for-bug compatible, but it's pretty darn close. So if you've written a lot of code to deal with the bugs that come out of the EC2 interface, it probably won't be the same thing in this. But it's getting there. Unfortunately, you had to do that. So now we've got a request come in. And we're not going to deal with it in the web server. That's the wrong place for it, because we want to get the request to come in, and then we want to get rid of it as quickly as possible. We've got these things in the back, the services, that are actually going to do all the work. So we've got our compute nodes to deal with the hypervisors. We've got the volume system to deal with storage. We've got the network services that are going to deal with making all the connections on our virtual LANs work. They've got to talk somehow. And when I say volume or network or compute, like I mentioned earlier, these are all plugins. So you can drop in any different implementation you want depending on what you're using for your network. If you want to do DHCP or you want to do flat IP addressing, you can do that. If you want to use different hypervisors, almost every group has an implementation for their different hypervisor. If you want to use Hyper-V from Microsoft, or libvirt or QEMU or any of these types of systems, you can do it. The big decision on your hypervisor, one is what are you using it for? If you're doing scientific stuff and you need to spin up instances that only live for a short time and then they go away, you might want to use one particular hypervisor. If you're a service provider and you want to mix and match Windows and Linux and you get licensing issues, you might want to look at something that can deal with that. A lot of people use KVM, open source, and a very good system. So when I say service, that's in a broad bucket. So now they got to talk somehow. So we use RabbitMQ. We use AMQP under the hood. By default, we use Rabbit. There is an implementation of ZeroMQ that works as well. So people familiar with queuing systems? Okay, good. So for those that aren't, a queuing system is it's like a radio station. So you subscribe to the channels that you're interested in. So if I want to listen to a new server got created channel, I tune into that. If I want to listen to networking events, I tune into that radio station. And when those events come in, then I can do the work on them. The nice thing about queuing systems is that it takes care of that headache about saying who's going to do the work, because everyone can listen on the channel and only one person gets that piece of information and they do the work on it, which is handy. So now we've got to get that information onto the queue. So when you look at the Python source tree for this sort of stuff, for any service, you might see like a network directory for network code. And there's an API, an API.py file for every one of these. And that takes care of all the marshalling that you have to do. So if I want to create an instance and I want to do it on a compute node, I can just say import novacompute.api, and then there's a method in there or a function in there that just says create instance, and I can say create instance, and it'll do all that stuff about getting it over the wire and sending it down to the appropriate node. So any service can talk to any other service relatively easily. This is a sort of a poor man's RPC protocol is what we're using the queuing system as. And people look at that and go, well, why are you doing that? Like, why are you trying to do RPC over a queuing system? It doesn't seem to make sense. But it actually has some surprise benefits. One thing that it gives you is it gives you a buffering system. So when the load comes, when you get that big spike of a load hitting the API servers, the queuing system can just queue it up, and then the workers can start picking it away. Now, if you had to do that with a normal binary RPC protocol, then you're into all the threading issues, and you've got to deal with your worker pools or your thread pools and everything. With this, you let the queuing system take care of all that, which works really well. It's sort of like when you see a flow of water coming down a hill, and someone puts a dam in front of it, and they hit the dam. All that water's got to go somewhere, so they put these big towers next to it where the water can go, when it hits. And that's basically what the queuing system gives you is the ability to buffer those surges that you get. So when someone from NASA says, I want 5,000 servers, the whole thing doesn't fall apart. Then the last piece is, well, not the last piece, but one of the other pieces is the scheduler. The scheduler is the piece that looks at all the different services that are out there and says, okay, here's what you've got. You've got this much memory, you've got this much disk, you've got this much network available, here's how much storage. And when a request comes in and says, look, I want a 512 gig or 512 meg server with 40 gigs of disk, and I want 3 cores on it, then the scheduler can go, okay, you pick from any of these, right? And then it does a little system called weighting and filtering. So it weighs all the servers to say, this one's pretty good. And then it filters out the ones that just can't do it. And then it picks from the list of that. And it'll send it out. And if it can't do it, it'll send the request off to that server. And if it can't do it, it'll come back and the scheduler will send it off somewhere else. So you can make your own scheduling rules, basically. You can plug in your own rules in there and say, here's how I want to distribute my servers as they're coming in. And the last piece is that we've got to get information back out to the caller. So we have all of these services, as they do something, there's a special radio channel here, a special queue in the system that sends out notifications as stuff happens. So you can subscribe to those if you're interested and find out, oh, my network is up, or my server is ready, or it just crashed, or my snapshot didn't work. You can find out all that information. That's typically where billing and stuff taps in as well. So that architecture is really good up to a point. You've got certain limitations in here. typically around the switch. The switch is probably the Achilles heel in a lot of this. You're creating a lot of virtual LANs, you're creating a lot of virtual networks, and there's only so much you can re-put in that. And then, your data center, if we can get probably, let's say we're going with the 200 instances per compute node scenario, that's a lot of racks and a lot of servers and things. So we need to scale this up. And also you need geographical redundancy. You want to have your data center in London, a data center in Chicago, a data center in Hong Kong, and they all have to be able to communicate. So this is where we get into a concept of cells. And this is how we scale this thing up even further. So we take this entire system and we just take the worker nodes and we put them down into other cells. And there's a special scheduler that works at the top level cell, and it forwards the requests onto child cells. So now the child cells can do their work. They can worry about their LANs and all their network issues and all the rest of it. Some things they do share. They'll share the database. They'll share the authentication system, some of the imaging stuff. And that's things that we want to break out. Right now, there's no easy way to solve that, but that's what we're working on, is finding ways to do that. So let's just look at a simple call. So here's a curl request for authentication. So I pass in a JSON payload that says, here's my username, my password, and a well-published API endpoint that I talk to. And I just do a post to it. And I mentioned before, you'll get back a token and you'll get back a service catalog. And the service catalog will tell you, now you can go to this place. So this is where this new endpoint is. So this would be a Chicago data center. I've got a tenant ID, which is me, not just my user, but I can be an employee inside of a company, so I have a tenant ID. And I just do a post if I want to, or this is a get, I just want to do a get on the flavors command. And the flavors are what type of server is it. So you can pre-can a whole bunch of different server types. Here's 1 gig of RAM with 100 or with a terabyte of data with 4 cores, and you can have a whole bunch of flavors for all different types of servers that you want to create, and you get a list of those. And then you can get a list of images, and these are all basically your ISO files or a snapshot that you've already created. I've created a server, I've installed all my software on it, I've got it looking just the way I want it. Now I just want to cookie cutter that thing like crazy. I take a snapshot of it, and then that'll show up on my images list. So when we want to boot an instance, we do a post on the servers, and we pass in a reference to the image, which is a UUID, and we pass in the flavor reference that we want, so whatever flavor 2 is. And we'll get an ID back, which is an instance UUID, and then we can just wait for that thing to spin up. Usually it takes a couple of minutes, depending on the server. So that's a lot of stuff, I realize. But if you want to play with this, the easiest thing to do is just find an old server. Don't try and download the source right from the site, and it's like trying to build a kernel. It's just a lot at once, a lot of flags and things. DevStack is a great way to get started. This will do all the heavy lifting for you and set up a dev environment on your laptop or on a machine or whatever. So you can get in there, everything's running, you can run commands against it, you can spin up servers. This is the way I would recommend that you get started. And then from there, you can start worrying about, let's make something a little bit bigger, a little bit more robust. But it's a great way to get started if you want to run the tests and maybe submit a patch. If you are really interested in this, we do design summits every 6 months. We started off October 2010 with our first one, and then they were sort of hodgepodge in between there, but then we settled on a 6-month schedule to coincide with the Red Hat and the Ubuntu guys, and to make our releases match with theirs. So Grizzly is our next release. It's all alphabetical as we go out. The first design summit in Austin was in Austin, Texas, and we had probably about 75 people show up. This last one, Folsom, which was in San Diego, we had about 1,600 people show up. So this thing is growing like crazy, and the number of companies in it is just going through the roof. This is a picture from one of the summits just recently. If you just do some Googling for OpenStack-related jobs, as of about last week, there are over 900 open positions that were talking about OpenStack. And that's all Python. So there's a lot going on there. Some references if you want to, hang out on the IRC channel and see what's going on there. Some of the main URLs. The QR code at the beginning of the presentation is a link to the slides. So if you want to take a picture of that. I know it was a fire hose in the face, but if you got any questions or anything.
So I have a question about the hypervisor that will be used in this. I understand it's not really open source, is it?
So the question was, are the hypervisors open source? Some are, some aren't. KVM is open source. Citrix has one called Zen Server Classic, which is open source. So there's some out there, but other ones, like the Microsoft one, is not open source. VMware is not open source.
So creating the images, so we can use those to create images for
Yep.
our instances.
Yeah, you can use any of those. There's a standard format. So the question is can we create images and use them between different systems? Yes, there is a format called OHV, which is Open Virtualization something. But anyway, you can put it in OHV format and use it on any of these. You can just yell out if you've got any questions. I can repeat the question rather than have to come up to the mic. No? Oh, got one here. It's a long walk, isn't it?
Yeah. This might be a little bit off topic, but what's up with Zen? I mean, I used it years ago, and it was a real pain in the ass to set it up. Then KVM came about with all the CPU support, and I kind of switched there, but I thought it was dead technology, if not for Amazon that keeps using it. So.
Yep. So the question is what's going on with Zen?
Yeah.
And Zen is alive and well. It's obviously they're putting most of their effort behind their Zen server product. Zen Classic is still alive and well, still supported by the community. But all the bells and whistles and the sugar on top comes with their commercial product. But KVM, a lot of the focus went towards KVM now, and that's where a lot of people are. A lot of the OpenStack stuff is using a pure open source stack, top to bottom.
Hey. So if there's no other questions, we're going to take a break until 1:50. When Andrew Francis will be talking about how to solve a problem like Santa Claus. I'd just like to thank Sandy for his talk.
Thank you.